Welcome to the second class of this module, where we shall discuss Monte Carlo algorithm in much more detail, so that by the end of today's class you shall be able to write down a simple Monte Carlo algorithm on the computer and be able to model the Ising model. Before I go on in today's class, let me give you a 2-minute recap of what we discussed in the last class. In the last class, we discussed that we are going to learn about Monte Carlo simulations and in particular model the Ising model and implement it on the computer and look at the change in the magnetization of a lattice of atoms as a function of temperature, and through that we basically understand the ferromagnetic transition from such that a magnet which is in a magnetic state at low temperatures goes to the disordered state at higher temperatures. So, we have Ising model is essentially a microscopic model to describe this phenomena, and using statistical mechanics and using model of this one can basically monitor the thermodynamic quantities like energy, magnetization, specific heat capacity and chi, the susceptibility chi as a function of temperature, and at the transition temperature, which is Tc, the critical temperature at which the ferromagnetic to paramagnetic transition occurs. These quantities show a certain change in behavior. Basically, the order parameter magnetization goes to 0, and that is how we characterize the so called critical temperature. Cv and chi show other properties, they will show peaks, but we shall discuss this in greater details. The question is, how do we model all this physics, all this statistical physics on the computer? A primary question is also that why do we need to model all such stuff in the computer? The Ising model can be exactly solved analytically in 1D and 2D. So, let me tell you what does it mean by solving the Ising model in 2D. It means that you can calculate the partition function. Using statistical physics, you can, if you calculate this partition function, you know that all other thermodynamic quantities can easily be calculated from by taking suitable derivatives of the partition function. That is what we discussed last time, right. Now, if you have the Ising model Hamiltonian, you can exactly calculate the partition function. Onsager did it way back in the 1930s or 40s, and you can exactly calculate Cv, E, M, all the thermodynamic quantities as a function of temperature, and so you can essentially understand how the Ising model behaves. You might already have done a mean field version of magnetic transitions, ferromagnetic transitions in your statistical mechanics class, but a simple model as simple as Ising model, where you basically have a spin which is interacting with just its neighbors, just its 4 neighbors in 2D and maybe 6 neighbors in 3D if you have a cubic lattice. In 3D, the Ising model is not solvable till date. You can only do it either using on the computer or extremely advanced analytical techniques, which where also you will get you will need approximations. Okay. So, just as so the point I want to say, emphasize on is that of course, you can exactly calculate the partition function of an ideal gas, you can calculate the partition function of an Ising model in 1D and 2D exactly, but as soon as you go to slightly more complicated Hamiltonians, interaction systems, you often need the help of computers to be able to exactly understand, which means calculate the thermodynamic properties in a and relate it to the thermodynamic physics. You need help of the computer, you can't do it exactly more often than not. Okay. and through this calculation you are basically trying to understand how you are going to do it, how you are going to do Monte Carlo simulations for more complicated Hamiltonians. So, Ising model is basically one of the simplest Hamiltonians. If you understand that, how to implement that, the principles of calculations remain the same, other complexities due to the Hamiltonian increases. Okay. So, with that background, let us get down to actually discussing what is the broad flow chart or what is the algorithm in basically modeling the Ising model on the computer. So, what we need to know, as you know, as we discussed last time, that basically spins on a lattice can be described by, I will just remind you, an array, a two dimensional array of L cross L, L being the size of the lattice, and what one has to do is basically at the beginning initialize the lattice, which means give values to these different elements of this array as plus 1, minus 1, whatever you whatever be the you want the whatever way you want to initialize the lattice. Of course, your final thermodynamic state does not depend upon your initial state. So, after initializing a lattice, you have to equilibrate your lattice or your system which you model on the computer for a particular temperature. So, you have to reach the equilibration state. So, basically you have to do a few Monte Carlo steps of your system. So, you have a few iterations of your system where you evolve the system, so that the system first reaches equilibrium, and once it has reached equilibrium, what you are doing essentially you are generating different micro states of the system on the computer. So, the system is accessing different micro states, and basically in the Ising model, as per the algorithm that we discussed in the last class, you are essentially modeling or you are using the canonical ensemble description of the Ising model on the computer. Why? Because energy can fluctuate. Basically, the energy of the lattice can increase when there is a spin flip happening. It could either, the total energy of the system could either increase, or it is possible that it could decrease, in which it is giving away energy to a bath essentially, right. And while generating, so once you have reached equilibrium, you can have basically n MCS, n for the number of Monte Carlo steps at a particular temperature where the system accesses different micro states, and as the system accesses these different various micro states, you can use those to calculate different thermodynamic quantities. Thermodynamic quantities like the average energy, say, or the average magnetization, or the average CV being the specific heat capacity, or the susceptibility, the average values. These are averaged over, these angular brackets imply average over different microstates. You are taking a basically an ensemble average, right. Now, how would you calculate these averages? As the system accesses different microstates, different spin configurations, basically the expression for the average energy here is the summation over different microstates k, the energy of the microstate. So, after every one Monte Carlo iteration, every 1 MCS Monte Carlo step, there will be a certain configuration of spins in the lattice, which will correspond to a certain value of the energy E I, right. And the statistical physics formula is essentially the energy of a microstate into probability of accessing that microstate, which is given by e to the power minus beta E I by z, z being the partition function. This is the so called probability of accessing a particular microstate in a canonical ensemble, right. But here in our case, as we discussed, we are doing a biased Monte Carlo simulation. So, what is a biased Monte Carlo simulation? We are basically accessing different microstates with the probability e to the power minus beta E I by z, right. Why that, we will discuss it later, but the algorithm which I discussed last time, that already ensures that different microstates are being accessed with this probability. So, this is what I told you, that in the metropolis algorithm, various microstates are accessed with probability e to the power minus beta delta I. It is a biased Monte Carlo, all microstates are not equally accessed. We are already using the background physics that we know to access different microstates. Now, since different microstates with higher and higher energies are accessed with lower and lower probabilities, once a particular microstate has been accessed, basically the average energy of the system is the sum of all the energies that the system accesses, all the different energies as the system goes on from one microstate to the other, sum up all the energies and divide by the total number of Monte Carlo steps NMCS that the system remains in that particular thermodynamic state at that particular temperature, right. And you can control how many iterations you want to give for the system to remain in that temperature. So, in how many microstates you want to generate at a particular temperature, right, and you can control that, and how this is done and how this is chosen, we shall discuss this later. So, once you have calculated the thermodynamic quantities at a particular temperature, what you can do is change the temperature, right, and allow the system to go to equilibrium, equilibrate at a at this new temperature, generate different microstates at a different temperature, calculate average energy, magnetization, CV, chi, etc. at that new temperature, and keep on changing different temperatures. You keep on calculating these quantities at different temperatures after suitable equilibrium. Then what we do is do the physics, plot and monitor these various average quantities and how do they change with temperature, and extract the physics out of it. So, this is the basic broad flow chart of what we shall be doing, right. Having discussed this, immediately you should be having quite a few questions, such as that how do we know that the system is in equilibrium. So, you have a lattice, you are generating different microstates as per your metropolis algorithm. When do we know that the system is in equilibrium? How do we know that the thermodynamic averages that we have calculated over a certain number of microstates, they are good and reliable? How do you know that you do not need to generate more number of microstates? After all, statistical physics tells you that basically the number of the ensemble average, I mean you have nearly an infinite number of microstates accessible. So, have you done a good thermodynamic averaging or not? Third question, what about finite size effects? After all, we will be calculating or doing our simulations over a finite lattice. It might be 20 cross 20 or 100 cross 100 or 1000 cross 1000. If you are doing a 3D 100 cross 100 cross 100 lattice size is already 1,000,000 lattice sites. You have 1,000,000 spins, which seems large for a computer, not for today's computer, but anyway it is a large lattice size. But what is 1,000,000 spins? In statistical physics, in a magnetic sample, you essentially have 10 to the power 23 spins sitting on a lattice, and you are basically interested to calculate the thermodynamic properties of a very large lattice, right. I mean, why do you think that if you do your modeling and calculating of thermodynamic averages over even a 100 cross 100 lattice, that is sufficient? So, that is what is basically finite size effects. We shall be discussing each of these topics as we go along in the course. As we model it in the computer, I shall be showing how does one check for equilibrium, how does one check for whether the thermodynamic averages are reliable or not. So, all these will be discussed, but let us start with finite size effects. even within finite size fx, there are two parts, I mean at least two parts. One could say that, well, there are boundary effects and the finite size of the lattice. So, we shall discuss this later, but let us talk about boundary effects. What do you mean by boundary effects? Well, you have in a experimental, in a real system, you have 10 to the power 23 atoms, spins, magnetic moments sitting in even a small sample, or if not 10 to the power 23, 10 to the power 21, which is anyway very large number. And then at the end of the sample, right. So, if you have a material of this size, say, then the end of the sample, basically those atoms are not surrounded by other atoms, but they are exposed to the air, say, right. But the number of atoms which are sitting on the surface of a sample, of a macroscopic thermodynamic sample, are relatively few, much smaller than the number of atoms which are in the bulk, which is basically where all atoms are surrounded by 4 atoms if you are talking of a 2D system, or 6 atoms if you are talking about a 3D system, cubic lattice. Of course, you could also have triangular lattices. So, we are not going into that at the moment, but assuming a square or a cubic lattice, what basically I am saying that if you are doing a 100 cross 100 lattice or a 20 cross 20 lattice, you have relatively large number of spins sitting at the boundaries, and that number is relatively comparable to the number of atoms which are sitting in the bulk, the number of spins which have atoms spins which are basically surrounded by 4 neighboring spins, whereas the ones on the right at the end, these ones, this, there are they have only they have basically spins only on one side and not here, right. And while we can neglect the effect due to the surface atoms on the in a real sample, can we really do it in this simulation? How do these show up? So, the way we get rid of boundary effects in simulations is that we use periodic boundary conditions. What is periodic boundary conditions? You essentially say that what, this atom. So, this atom has one neighbor which is this one. So, the neighbor of this atom is this, this, this and this, right. So, so there is a continuity. So, periodic boundary conditions you must have used also in your theoretical courses. Of course, this one has basically this neighbor, this neighbor, this neighbor and this neighbor. So, there is not a problem at all. So, here this is how we get rid of boundary effects in simulations. Now, let us say that this is spin I j. So, suppose this is I am talking of this spin and this is basically spin I j. So, that is how basically each site on the lattice is denoted by an array, and choosing I and j basically fixes a particular lattice site. Now, one could say that the neighbor on the right can be denoted by the index, the lattice index I plus 1 j. The neighbor on the left can be denoted by I minus 1 j, this being I j, this is being the spin of our interest. The spin at the bottom, right. So, it is like one layer is can be denoted by I. Now, while discussing this, let me first set the convention. I should have done this earlier. So, now let us suppose that the spin on this corner is 1 1, okay. And then as you go on the right, you are essentially increasing the index. So, that this spin is called L1, right. So, I plus 1, so this is 2, this is 3, whereas the second index j remains the same. So, this is L1, call this one essentially 1 L. So, basically y is increasing in this direction and this is L L. So, in this convention basically the right neighbor of this one is I plus 1, the left neighbor of this one is I minus 1, the down neighbor of this is I j minus 1, and the one which would be here on the top would be j plus 1, I j plus 1. Yes, but you have a problem when you implement periodic boundary conditions, because the neighbor of L 3, suppose this is L 3, right. So, this is L 3, the neighbor of L 3 will be 1 3. So, it is basically this one, and the neighbor of 2 1, right. So, what is 2 1? It is basically this one, right, will be 2 L, which is this one, right. So, when we calculate the neighbors and identify the neighbors, we have to be aware and be careful about periodic boundary conditions, and this is how you identify neighbors. We shall see that in the code also later. Okay. So, the next thing to discuss before we actually move to the computer code and show how the algorithm is implemented is the issue of units. What do I mean by units? You already know that basically we are looking at magnetism. Basically what is, so we should be looking at the magnetic moment, but we know that the magnetic moment is essentially related by the Bohr magneton to the spin of the system, right. And I have been telling you that the spin can either point up and down, and we will take its value to be plus 1 if it is pointing up and minus 1 if it is pointing down. But actually the spin of the system of an atom, say, is measured in units of angular momentum h cross, right. So, when we say that the spin is plus 1 or minus 1, we are basically setting h cross equal to 1. After we calculate the magnetization, we have to put back the units of spin, which is an h cross, and basically from the spin we can go to the magnetic moment by multiplying suitably by the Bohr magneton. But all those are essentially set to basically we are ignoring that, we are saying yes, the spin is just plus 1 or minus 1 instead of saying say minus half h cross and plus half h cross, right. So, that is all hidden for the purposes of the simulation. Of course, for the real system it is there. Moreover, we are measuring magnetization. When we use the word magnetization, we actually mean magnetic moment, which is the magnetization at a particular temperature will of course have units of magnetic moment, and we use magnetization as the order parameter, but for purposes of the calculation we measure magnetization as the magnetic moment at a particular temperature, which is essentially this angular brackets again represent the canonical ensemble average divided by the maximum magnetization possible, which is can be only at 0 temperature, right. And this can be related to the average spin of the, so average spin of the system at a particular temperature divided by the maximum spins, if all spins were basically pointing in the same direction, say in the positive direction. So, that would be the S max. So, basically the number of spins on the lattice into plus 1 say, and we use this normalized quantity as the order parameter to calculate the statistical physics, right. But of course, the units are there, though in the code we will not be really worried about the values of very small numbers like the Bohr magneton and h cross. Why? Because we can put it back in the calculation after we have finished our calculation, and we do not want the computer to deal with very small numbers as that will decrease the efficiency. So, you calculate it in so called simulation units and put it back when we want to compare with experiments. Talking about order parameter, you already know that the maximum value of the order parameter, we have defined it in such a manner by suitably normalizing it, that at low temperatures the order parameter is nearly equal to 1 or close to 1, and at exactly t equal to 0 it should be 1, which means the system is perfectly ordered. There is no thermal fluctuations. Of course, there are quantum fluctuations, but we are at the moment treating the system classically, which means that h bar goes to 0. We are looking at only the thermal effects. So, for a classical spin system at t equal to 0, the order parameter magnetization will be equal to 1, which means it is perfectly ordered. All spins are pointing in the same direction, and that is minimizing energy. Actually, I remind you, and this is extremely important, in a thermodynamic system, what is minimized is not the energy, but the free energy. But at t equal to 0, the free energy is u minus T s, t is equal to 0. So, energy minimization happens when all the spins are pointing in the same direction, whether it be plus 1 or minus 1. But at any finite temperature, the minimization of the free energy will be decided by u minus T s, the entropy of the system and the temperature as well, and that is why after all we get the phase transition. We will understand this better as we actually code it and we see the effects. Anyway, because of the effects of entropy at high temperatures, the what will matter in the minimization of free energy is not the contributions due to E, the average energy, the average internal energy, but rather the minus T s term will dominate. It would rather the system will prefer to basically be in a disordered system. So, that S is minimized through the minus T s term, right. So, that is what it means. So, that dominates over the internal energy, right. Contribution of minus T s dominates over the internal energy, and that is how free energy is minimized. Now, how to calculate average energy? So, we discussed order parameter here. Just to remind you, we also so we discussed order parameter, magnetization, magnetic moment. The other quantity of interest is essentially the Hamiltonian, right. The energy comes from the expression for the Hamiltonian, which is basically minus j Si dot Sj, where the summation is over all the, where I goes from 1 to n, n being the number of spins in the lattice L cross L, and the summation over the nearest neighbors, j goes from 1 to 3 4 in a square lattice, right. And we also need to discuss what is going to be the units of energy, and what is energy. Essentially energy is this average value of this quantity in the center, and this so this is basically the, so this quantity within the angular brackets is going to determine the spin of a particular microstate or the spins are going to be arranged in a particular manner at the end of one Monte Carlo step, and that will depend the instantaneous energy of that lattice at the end of a microstate. And to calculate the thermodynamic or the average energy, right, one has to do this average over different microstates, basically take an ensemble average. You generate different microstates and calculate the energy averaging over these microstates, right. Now, we have to also discuss the units of energy. Now, you know that this quantity j, so Si and Sj, you call it plus 1 and minus 1, And if you are saying that you want to calculate the average energy, then the units of energy are essentially sitting inside this minus j. This is minus j has all the Bohr magneton, this, that, everything, and so j we shall be using as a parameter, but the value of j for different systems, cobalt, nickel, iron, you can also get it using quantum mechanical calculations, right. And typically j is measured in units of electron volts by doing the suitable quantum mechanical calculations, right, by putting in all the electrons, all the various degrees of freedom, but here we are interested only in the magnetic moment degree of freedom. The other unit of energy which is relevant in the problem is kBT, thermal energy, right. It is basically a competition between as I said U, which is determined by minus j si dot s j, and the entropy of the system, where the spins can take different configurations, minus T s. Now, how is kBT measured? Now, kB is the Boltzmann constant, you might be knowing, and that is written as R by Na, where R is the gas constant, PV equal to N RT, that gas constant whose value is 8.32 in SI units, whereas Na is the Avogadro number of atoms. So, Kb is R by Na, and Avogadro number of atoms, as you might should be knowing by this time, is 6.02 into 10 to the power 23. And this gives the value, if you divide, it gives 1.38 into 10 to the power minus 23 SI units. kBT has units of energy. You might have read in your statistical physics course that using the equipartition theorem, the kinetic energy per particle monoatomic gas is 3 by 2 kBT. Kinetic energy is essentially units of energy. So, kBT has units of energy, and kBT at T equal to 300 Kelvin, which is essentially 27 degrees centigrade, is 3 into 1.4. I have taken 1.38 to be 1.4 into 10 to the power minus 21, which is basically 4.2 into 10 to the power minus 21 joules. Okay. So, J is measured in electron volts typically, and kBT is measured in say joules. Now, we can't be working with different units. So, we have to set the units for our simulations, right, and we want to have a easy unit.